All right, so perpendicular bisector, maybe a picture would be enough for you guys on that. But perpendicular bisector, oh, that's not very good. We've got this line segment. We swing an arc up here, and then swing an arc down here and down here. And what we're doing is creating a 90-degree angle and two congruent segments. So maybe a picture would be a sufficient way to define this. But perpendicular bisector splits a segment in half. And hits at 90 degrees. And equidistant means literally equal distance. So equal distance. Let me try rewriting this again. So equal distance. So what our first theorem says from this section, it's theorem 5.2, the perpendicular bisector theorem. It says that any points along this perpendicular bisector, I don't care where they are, they can be anywhere on here. Any points along here are always going to be an equal distance from the endpoints. In other words, this is congruent to that. And then its converse is true as well. If you have a point that is equally distant from the endpoints, it is on the perpendicular bisector. So this is an if and only if theorem. They state it as the theorem and its converse. Remember, the converse is switching the if and then, but that's what it's saying. And so you'll have a couple problems where you have to apply this. You have to just find the distances or set up an equation and solve for x. So you'll be setting some things equal. Okay, that's about it. So perpendicular bisector theorem. It says in the diagram, MN is the perpendicular bisector of ST. What segment lengths in the diagram are equal? So we've got, well, the ones that are marked, right? TQ is congruent to SQ. And we've also got the ones that aren't marked but are still congruent. MT is congruent to MS. MT is congruent to MS. It says explain why Q is on MN. How do you know Q is on MN? Well, this is using the converse. It's based on the fact that these distances are the same. Okay, so I know Q is on MN because it is an equal distance from segments that are on the perpendicular bisector. So Q is on MN because it is, we'll use our new word, equidistant. I can spell it. Equidistant, that's the 12s, from points on the perpendicular bisector. That perpendicular bisector is TS. So it's equidistant from T and S. Therefore, Q must be on MN, which is a perpendicular bisector of TS. The perpendicular bisectors of each other, really, right? So we have two based on those distances. So that's it. I think it's a pretty intuitive sort of theorem. All right, and then they have one other theorem for us in here. One other theorem. It says the angle bisector theorem. So think about your angle bisectors that you've been constructing. It says if a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. That's just saying that anywhere along this ray, so if I have a point right here, and you draw a line segment there so that it hits that point at a right angle, and then you do another one over here that hits at a right angle. These 2 points are the same distance away from QS. QS is the angle bisector. So as you go along that angle bisector, there's a whole set of points that would match up with each other, being the same distance from that angle bisector to that ray. And then if a point is in the interior, or if a point in the interior of the angle is equidistant from the sides, that's talking about this point here, of the angle, then the point is on the angle bisector. That's theorem 5. So we got 5, 2, 5, 3 are converses of each other. 5, 4, and 5, 5 are converses of each other, and they have to do with those two constructions we just did the other day. Review. And tomorrow we're going to finish up that construction with, or revisit it, I guess, the one where we did the perpendicular bisectors of all the sides of the triangle and they intersected. Didn't quite finish that, but they intersected somewhere that was equidistant from the vertices of that triangle. So we'll draw our circumscribed circle around the triangle. We'll finish that one up. And then we're going to do the intersection of all the angle bisectors and discover something that's special about that point. We call it a point of concurrency. It's where all the angle bisectors cross. And there's something special about that. It ends up being the circumscribed circle, the circle that you can draw inside the triangle that just touches each of the edges of the triangle. That's where we're headed with this. All right, so this is the Common Core-ish thing here. Taking it the next step up, instead of asking, you know, what are the lengths of MR and RP, and they give you one of the lengths, they give you algebraic expression. And here we are again. We're either setting things equal or adding them up to equal something, right? What do you think we do in this case? You can tell from the picture, right? Yeah. But the theorem says we would set them equal. So 7x equals 2x plus 25, and then we would solve for x, and then plug in to get the length of Rn. So it's a little higher level. We've got to do some algebra. Subtract 2x. 5x equals 25. Divide by 5. X equals 5. But then it says find the length of Rn. So we go 7 times 5 gives me 35, so Rn equals 35, and so would Rp. Rn equals 35. That's about it. That was like a 7-minute lesson. See you in just a minute.